this lecture of today is about a work that I've been done with Nuno Baeta for some years now, about the prover, a geometry automated deduction prover. Namely, a prover based on the deductive database for geometry method. And also an effort of our part, and not only, it doesn't begin with us, it began with Predrag Janicic from Belgrade in Serbia, the Open Geometry Prover Community Project. So the first thing that we have to realize is that in geometry, there are two currents in terms of automated theorem proving. One is algebraic methods, the other are the synthetic methods. The algebraic methods began by converting everything from geometry, from a geometric construction to algebraic representation. That representation is completely already solved, sound. So whatever construction you have, you can put it in algebraic form. But then the proof itself is done poorly by algebraic methods, Grosvenor bases, and that kind of things. That breaks completely the connection with the geometry. So for instance, for an educational point of view, they are more or less a black box approach. You have a problem, you push a button, and the computer say yes or no. You can see the proof, but the proof is not geometric, is algebraic, and sometimes it's very hard to understand. After the second or third step, it's very difficult to follow. Even for an expert, it's difficult to follow. So, okay, synthetic provers. It's funny because in certain sense, the early approach in artificial intelligence, artificial intelligence was something that began in the 50s of last century. And it has a big burst, then almost died, and now is again very strong. But the first early moments of artificial intelligence was connected to geometry and automated geometry provers. Galantern and Coelho, a Portuguese researcher, made some rule-based provers that were very interesting, and they promise a lot. After some attempts to extend them more, it was difficult with the technology, with the approach that they used at that time. But synthetic provers are interesting even today for if we want to introduce proofs in high school, for instance. And we, myself and Joana Teles van der Sant, two colleagues more education-oriented in the department, we already made some effort in that direction, even with a real high school teacher and a class with the introduction of automated theorem provers in that class. And for that, we need that kind of provers, synthetic provers. So, for example, the geometric database method in GGEX. GGEX is a program, a dynamic geometry system with automated theorem prover in itself. It is very interesting because it has the two components and it connects very well the two components. You can see on the right the construction. The construction was made more or less like a normal construction of a DGS, of the dynamic geometry system, points, and lines connecting the points, and parallel lines. And on the right of the right, no, on the left of the left figure, you see the symbolic representation, not algebraic like in GeoGebra, but the production of that, it was not writing on the left and see the figure. No, construct the figure and see the symbolic representation. And we can, at a certain point, establish a conjecture. To prove the angles CBBA is equal to ADDC. And so pointing or putting the mouse in that, it shows the angles in question. It has an animation. And if we want to prove it, it produces a proof that is more or less readable. It is, okay, it's not the normal thing that high school student expect at least in Portugal, but it can be explained, and it is, for this case, very short. By hypothesis and by rule 2, you have one thing, by hypothesis again, and rule 2, another thing, and then combining by rule, I don't know what was the rule because I hide the rule by pointing to it. But by a given rule, it reached the conclusion. And even for a more complicated theorem, the Euler's line, it produced, of course, a more long proof, but nevertheless, it is very easy to follow. And it has, this program, very nice features, namely the connection. We pinpoint something in the proof, you can see, and you see animation or representation of that fact, of that step of the proof in the construction. And if you want to know something about a specific rule that is being used, you can ask, okay, give me the details of that rule. And it opens you see on the right, it opens a sub window with that explanation. Again, in terms of visual representation. What are the drawbacks? There are two drawbacks in these three drawbacks. The first one is that the rules, and we will discuss that in a second, the rules that are used are hardwired. They are on the prover. You cannot change them. It's not the case, for instance, with automated theorem provers, the generic automated theorem provers. You begin by providing the set of axioms and rules of inference that you want to use. And they have a generic mechanism to use that system of axioms and inference rules and your conjecture to prove it. Here, no, the rules are hard-coded, and there is no, one big question, there is no document stating what are the rules exactly. The lack of documentation is something significant. The other problem is that the program itself is discontinued. The effort of supporting this program was stopped. The community as a whole, in certain sense, are trying to renew this and to, in certain sense, rebirth this GigX because it's very interesting. The final drawback is that it's related to the first. The rules are hard-coded, and it seems that the rules are the normal rules, but it's not. It does not happen like that. The angle is a completely different angle. It's the full angle. One of the things that the automated theorem provers has difficulties is the angle between the angle is not between two lines, it's between two semi-lines. And so the angle is, if you say ABC, what is the angle of ABC? Is the small one or the big one? And this is very hard to the automated theorem provers to work with. So they solve the problem by saying that the angle is not between the semi-lines, but the lines. And it is a different notion of angle that for many situations it works. It is equivalent, but there are some situations where the full angle is not the same as the normal angle that the students are expecting. So one part of the work is to, the other problem also is that these are formal rules. The rendering of the rules, even in terms not graphical, but in terms of the rules, GGEX already do some nice work in these terms, but we have sometimes, or we would like sometimes to have high-level lemmas to apply, to forget the details and say, okay, this is true because we have proved that in another lesson. So one of the works that we have done, and building on the work done by Gagnon and Font in the CAS 2 tricks tutorial system, it was to see what are the rules that we want to have in high school. And Joanne and Wanda made that work, and they reach for a given set of problems that are problems that the students are in high school deal with. They found this set of rules. For the automated theorem provers, these are high-level rules, and of course they need low-level rules to deal with collinearity, parallelism, perpendicularity, congruence, and so these the rules at the end are a combination of the high-level rules and low-level, in certain sense, rules, saying, for instance, that ACB are collinear, so ABC are collinear. This is something that for a student is stupid to state. Okay, if we have 3 points, they are collinear, what the matter? But for a formal proof, one thing is to say ACB, the other is to say ABC. The order is not the same. So we have all these kind of low-level rules. And one of the question, it's to render the proof hiding in certain sense these details. The prover itself is the idea is to have forward chaining. So from the problem to the axioms, but that mechanism is already proved to be very difficult to deal with. We have to deal with explosion of cases, and the idea behind this deductive database method was and is to use the specifics, the procedures that deductive databases have to make that proof efficient, to make the finding of the fixed point, being from the problem to all the facts that are proved from that starting point. The deductive databases method try to have that in a efficient way. So Shu not only explain the mechanism, the algorithm, but also introduced a set of rules that they say were a good set of rules. And he made some guidelines on how to select a better set of geometric inference rules. We already saw that the set of rules that Shub presented is far from adequate. There are many things that are not well defined in the paper, and they are consistent, okay, at that, if not, they are garbage, but they are consistent. We have proved that using Vampire, but we are now in the process. It's a large we. It's myself from Coimbra, Predrag from Belgrade, Julian Arbu from Strasbourg, Zoltan Kovacs from Linz, and Anna Peteruyenko from I don't remember the city. He's from Poland. It's a new recent introduction in the group. So I don't Bialystok. I think it's Bialystok. Okay, it's a big group, and we will join in this next May to discuss this set of rules using the Europroof network cost action. Our idea is to go from the work from Shu, but to have a good set of rules and use, for instance, Coq to validate the rules and to see that everything is good and it's sound to be able to use. So this is something that we are on the process. We have a set of rules that are implemented in the GGEX. The set of rules described in the there is one problem that the set of rules described in the paper, SHU 2000, and in GGEX are not the same, but that is not said anywhere. The program is very complex, and it's not clear what are the rules of the prover. It's impossible. It's very badly documented, the program. So we are trying to, okay, this is a base, but maybe we don't want to be like Pisa Tower. We want to build on firm ground and not incline ourselves more and more. So what are the goals of the prover? Apart from that rebuild of the rules, we want to be efficient, and and now I'm speaking about the new prover that we are building. We have already a version working, but our goals in that prover is efficiency, flexibility, rendering, and open source. Open source, beginning by the bottom. The open source, we want to avoid that experience of hard-coded the rules in a given program. So we don't have, okay, GGEX is now not continued, it's discontinued. Let's go to GeoGebra. We don't want that. We don't want to have a prover that is hard-coded in a given program. So we are developing an open source, an implementation as a library, not a program. So something that can be connected, that can be used by other programs freely. And that is already done. Okay, it's completely open source, is in GitHub, and it is usable as a library. We have a small program that use the prover to test a test bench in certain sense, but the idea is to allow it to be used by third-party programs. The rendering is something that is, for the moment, not worked, but given that is a synthetic method, we believe that we can, on the same verge that the GGEX, we will have the possibility to have a proof and connection with construction, geometric construction, and it can be made rendered in a natural language as close to possible to the ultimate goal or the different clients that we have. Flexible, that is also something that we are now working. The idea is a bit like Vampire is a generic theorem prover, very well known now. It does not have the rules hard coded. They have the possibility to read the axioms and inference rules, for instance, Tarki's geometry, the rules of the database, deductive database method, or whatever, and make the proofs from that. GGEX, no, it is hard coded. So our idea is to have to separate the mechanism of the inference mechanism from the rules. And we believe that using the SQL approach, we will be able to do that. Efficient. Okay, we have to still live to that claim. For the moment, it is not that efficient, but we use not, of course, a server and a client SQL. If you know databases, if we use a server client model, all the efficiencies will go in the connection, and it is impossible to even control that efficiency of the connection. So we are using in memory as a library SQL database. So we have already a prover, and if we see the process of introducing new rules, these are more or less simple for once, and we feel that we can go to a generic prover capable of accepting a different set of rules. So for the moment, we have to, if needed, update the scanner, then if needed, update the table in the database, but these from a given point onwards, it will be not needed because we already have all the syntax constructors, so we don't need to change the scanner. The scanner is a flexer, flex bison construction is a grammatical recognizer. So we have to change the grammar, but at a certain point, this will be already fixed. And then we have to add to change the prover a bit in different steps, but these are not that difficult. And our goal is to have a meta prover or a program that can make that conversion from the rules in a given format to the internal mechanism of the prover, and after that the prover can proceed. So the prover in the current version use the first order format of the TP, 1,000 of problems theorem, 1,000 of problem for theorem provers of Sutcliffe. And there is a story behind this, and it is now a sad story in certain sense, because there were some years ago cost action trying to push the idea of a common format for geometry. So they reassembled all the guys that were working in a dynamic geometry system. And I don't know if in Italian you have the expression sack of cats. In Portugal, when we want to say something that is completely impossible, is to put a pair, 3 or 4 cats in a bag. They will fight to the death and they will not produce anything. And it happens that way. And I lost many months of work trying to extend that common language of dynamic geometry system to the provers. But then I realized that I cannot extend something that is dead. And after they produced that system, but after 1 year, 2 years, all the developers of the DGSs forget that that format. So I look on the other way, and the first order format of TP is more or less is strongly accepted by the community of automated theorem provers in general. So I decided to go that way, and I already have in certain sense the support of other researchers in the community to go that way, and forgetting the intergeo common language that is now completely there. And our prover, we converted all the rules of the SHU 2000 to this format. We have a module in TP about that. And so we can feed our prover with something that came directly from TP, the database. And for instance, this problem, simple problem, the prover is able to prove it in 0.0009 seconds. And if you remember last talk, I talked about fixed point, to be able to find all the things that are possible from that construction. Okay, to find the fixed point, it is not so efficient as 56 seconds, but nevertheless, he was able to do that. But for the moment, it's still 0.6, 0.7, meaning that there are still plenty of efficiency and other issues to improve the prover. So these are the second part of my talk of today, is the Open Geometry Prover Community Project. This is something that began some years ago by Predrag in Belgrade, Serbia, and now I make my contribution also. And the idea is to have to stop the actual status of tools having hard-coded the provers to a more open source idea, to be able to be usable by third-party programs, and to create the sense of community in terms of development, avoiding the disparate efforts of many researchers trying to implement the same methods again and again without being very useful for others, because for instance, the area method I helped, and I'm the co-author of one prover of the method, the area method, with Predrag Janicic. But again, it is hard-coded in one tool. If you want to use that method, you have to use that tool. And the idea is to go for open geometry prover that can be a house for all the developers. So what are the goals? To provide a common open access repository. We already have a GitHub repository where we put our work, and other begin to have its sources also. To provide an API, an interface with different automated theorem provers in such a way that they can be used by as standalone or integrated in other tools. To develop a portfolio strategies. This is something that I don't have I'm not very experienced with portfolio, but Zoltan Kovacs already has this. The question is that what is this portfolio strategies in automated theorem proving? Is a meta program that can, for a given problem, can put several provers working in parallel, and at a certain point give, okay, this is the best prover that you can expect to have in this for this problem. Again, let's go all the way with this prover. All modern automated theorem provers use this kind of portfolio strategy, not to have one method applied from the start to the end, but to be able to, for a given problem, select several, try them in parallel, and at a certain point, okay, the proof made by this one. And we have, for instance, in geometry, again, this is, sorry, very doable because of one thing, that we have algebraic and we have synthetic. The algebraic are very efficient in terms of speed. So they can be used to, in a first level, a first stage, to say it's true or not. But then rely on a synthetic one to give the proof itself. So we want to incorporate these to interface with repositories. Now I already have the TGTP, 1000 of geometric theorem provers, something similar for of the TPTP, but for geometry, and it has in the server that is based a program that is always listening. And if we can provide clients that, for instance, put it inside a GeoGebra, can ask the server, okay, give me problems of this type. And the server will reply with the programs, the problems that are of certain kind. So we already have these, but of course it should be improved. And we began to develop a GATP system competition. This is also in the line of the CASC competition. I don't know if you know that is for automated theorem provers. There is always a competition in the annual conference of the community, the CADE conferences. And the competition is always, it's something that is interesting. Okay, it has two ways to see it. Sometimes the competition itself does not help anything because it's a bit like benchmarks in the past. At a certain point, the benchmarks were completely useless because the programs and the ships were done specifically to beat the benchmark. But this competition, the idea is to have something that can be useful to improve the quality of the automated theorem provers in the area of geometry. We began to have that. I don't know if we will continue, but we had a first and second edition. This last ADG, we didn't do it. I don't know. OGP, CP, actually, or in the current version. So we have the prover and we have external provers, and we have developed the connections between the external provers and also the repositories. It is hosted, as I said, in GitHub. It is open sources, and okay, it's a unique kind of thing. We, for the moment, we didn't any effort to support Windows. I have, okay, and small between commas. I have several definitions of happiness. One of it is to be free of Windows. I'm very happy to be a Linux guy for many years. And so for the moment, we have no support of Windows at all. In Linux, it's very easy. It's make and it's done. Maybe in the future I will not do it myself, but I can maybe have a PhD student or something will do it in Windows. The API application programming interface is already have some filters to go from one format to the other. For instance, if we want to use this in GeoGebra, of course we have to have a filter from GeoGebra to FOF, to first order format, and vice versa. So we have already developed some of the filters, but the idea is that each developer of a given third-party program will maintain and develop the filters. So we have some filters. We already have incorporated in this effort Zoltan Kovac's GeoGebra automated reasoning tools, GCLC Predrag Janicic, the Coq area method Julian Arbu, and GigX is we did that without the help of the authors, but GigX, as I said, it's now we have an effort, a going effort to pick up GigX and renew it and try to work on it. It will not be easy, but Zoltan is working very hard, and I think it will be interesting to see if he succeeded. So portfolio, I already talked about this. The interface with repositories is done with TGTP, and it has a server client architecture. It's a very simple thing to send a query to the server and the server answering, but and the server has a program running a bit like a web server. It is listening always in the given gate. This is a program of this type, and it is working. The competition. So what are our problems, our expectations. The problems related to the integration between different geometry provers are not easy. We have, for instance, many axiomatic system tasks, Hilbert's von Plato, area method, full angle method, and sometimes it's not possible to have the conversion or to expect even that we will find an axiom system that run or that will win the competition. So it's a question that we have to deal with. Different geometries. In terms of 3D, there are very few things the authors of the full angle method, the area method, tried to go to see the 3D, but they didn't end that work. Filip Maric from Serbia works have several works around non-Euclidean geometry, and also the different approaches: synthetic, semi-synthetic, algebraic. So it's not realistic to have a full integration of all these things, but the question is to have a place where all the community, and we are not that large community where we more or less know all each other. So the idea is to have a joint work avoiding separated efforts. And okay, obrigado from Portugal. Gracias, because there is a Spanish community strong in this area. Merci, because there is a French community for Danke, Linz. I forget the Serbia, because I don't know how to say it in Serbian. And gracias.